Hey everyone, welcome back. This is week 18, and we're still working through the Boyd book. So this week I finished last section of this chapter, which is 4.7, which is on vector optimization. So this one's a bit of a conceptual, departure from everything we've been doing so far. Up until now, every single optimization problem we've looked at has had a scalar value objective. So it's one, real value number we're trying to minimize. But section 4.7 asks a different question. What if you take your objective that takes on, multiple values in R of Q space? What do you do then? So what even is a vector optimization problem? Well, as you can probably imagine, it involves generalized inequalities. So the general form looks like the following. So it looks like a regular optimization problem with this objective here and these constraints. However, now we have this with respect to k, where k is a proper cone and x, this function here is evaluated on R of q. So before, f of 0, x would evaluate to a real number, but now it's in the R of q space. And as we've seen before, k has to be a proper cone because it tells us how to compare objective values. So we use the generalizing inequality induced by k. So in other words, if x and y are both feasible, we say x is better than or equal to y if f of 0x is less than or equal to, with respect to k, f of 0y. The big thing that makes vector optimization different from scalar optimization is that two objective values don't have to be comparable, actually. You can have a situation where neither f of 0x is less than or equal to f of 0y with respect to k, nor f of 0y is less than or equal to f of 0x with respect to k. So in the scalar case, that's impossible. You can always compare two real numbers. Here is not just possible, it's actually very common. So we saw this back in chapter 2 with generalized inequality in cones. So this incomparability is the root of everything that's interesting in this section. So now let's define the set of achievable objective values. So the set of achievable objective values is simply just the values that f of 0 can take such that x is feasible, meaning f satisfies these constraints here. And of course, it must be a subset of R of Q. Now, this is just the image of the feasible set under f of 0. So keep this in mind. It's the geometric object, this big O here, that everything else is talking about. Now, the cleanest case is when the achievable set O has a minimum element. So a minimum element is a single point that's better than or equal to everything else under O that's less than or equal to anything else with respect to K. So this might not always be true because this assumes that it's actually comparable to everything else in the feasible set. But if it is indeed true, we call this the optimal value and the corresponding x the optimal point. So concretely, x star is optimal if and only if x star is feasible and the set O is a subset of this objective function evaluated x star plus the set k. So the interpretation is that this right side f of 0 x star plus k is the set of all values that are worse than or equal to f of 0 x star. So the condition says every achievable value is worse than or equal to the optimal one. This is exactly what the minimum element means. Okay, so here's a diagram just to illustrate what I mean. So this green sort of box extending on to infinity is the starting point plus k, which is in this case r of 2 if you look at it carefully, and the optimal set, feasible set is this blue region here, and we can see every single point is worse than this point here because it's to the right and above this point. Now, again, this is a very special situation. Most vector optimization problems don't have something like this. Now, the more general and practically relevant case is the Pareto optimality. So this is a case where you have a value that's not comparable to every other value in the feasible set. So we say x is the Pareto optimal if f of 0x is the minimal element of 0, not the minimum, the minimal element. So this distinction matters. So the algebraic condition is x is Pareto optimal if and only if x is feasible and f of 0x minus k intersect 0 is equal to the set, which contains a single point of f of 0x. So let's break this down. So the set f of 0x minus k in these parentheses here is a set of values that are better than or equal to f of 0x. So this is saying the only achievable value better than or equal to x objective is x objective itself. So we can't do strictly better. Okay, so here's a diagram that demonstrates what I mean, or what the textbook means, I guess. We have this point here of interest, f of 0x, PO, which is Pareto optimal, and all the points here, f of 0x minus k, are all points that are better than this point here. But none of these points here are in the optimal set, or sorry, in the feasible set. So this set of 0x minus k intersects with this point here only has one element, and that's itself. So that's why it's a Pareto frontier. Now notice a different geometric picture between the minimum and minimal elements. This is what you should keep in mind when we talk about these things. So unlike the optimal case, there's typically a whole set of Pareto optimal points, what's called the Pareto front. So that's this dark blue line, which are all sort of Pareto optimal. And also the textbook notes that every Pareto optimal value lies on the boundary of the optimal, the feasible sets. So hopefully that's geometric intuitive. If a point were in the interior of the feasible set, you can nudge it sort of in every direction and still stay in the feasible set, so you can find something better. Okay, so now, proto-optimal points are very nice, but how would you actually go about finding them? So that's what scalarization is all about. So the idea is actually pretty simple. First, you pick any scalar that's strictly positive. So in this case, lambda. And you do so in the dual cone sense. So if you go back to chapter 2, we talk about dual cones, and then we solve the ordinary scalar problem. So first we just choose a lambda that's positive with respect to k star. That's the dual cone of the proper cone k. And then we have this scalar optimization problem. So it's not an optimal a vector optimization problem. It's a scalar optimization problem now. And of course, we're very familiar with scalar optimization problems. We can readily solve it. Okay, the claim is that any point of the scalar problem is a proto-optimal for the original vector problem. Now, I'll say that again because it's very important. The claim is that any optimal point x from this scalar problem is a proto-optimal for the original vector problem. So all we need to do is choose a lambda in this dual cone, and we could find a proto-optimal in the vector optimization problem. Now, this is a huge result, but let's see why it's true. And actually, the proof is short, so I'll walk you through it. Okay, so what you do is you do proof by contradiction. you first suppose that x solves the scalar problem here, but is not Pareto optimal. That means that there exists a feasible y such that f of 0y is less than or equal to f of 0x with respect to k, and f of 0y is not equal to f of 0x. Why is this true? Because x is not Pareto optimal. So there must exist a better solution, y. Okay, so that means that f of 0x minus f of 0y is in the proper cone k, which, not including 0, because they're not equal. And since lambda is greater than or equal to 0 with respect to the dual cone, by definition of the dual cone, we have this expression here, and this contradicts the fact that x is being optimal for the scalar problem, because we know that there's another value y, which is more of a minimum. This is the objective value here. We want to minimize it, and if we can find a different value that's smaller, then this contradicts the fact that x is optimal. Okay, so let's look at the geometric picture of what's going on. So solving the scalarization problem here, what you're really doing is you're finding a supporting hyperplane to the optimum set. So the feasible set. I keep saying optimum, but you're finding the hyperplane to the feasible set at x f is 0x. So here, this lambda here, here's one solution that points in this direction. So this is the hyperplane here, and you found a solution. So the weight vector literally tells you the orientation of the hyperplane you're pressing against the achievable sets. Now, notice I've included this sort of rough jut here right in the middle, and if you think about it, you can't actually find any hyperplane. This dotted line is maybe the best you could do. That contains all of the optimal set on one side. So this is a fundamental limitation of scalarization for non-convex problems. Now, of course, if f0 is k convex and all the constraints are also convex, then the scalarization problem is also convex, and you won't have to deal with something like this. That's another reason why we like convexity so much. Okay, so let's make this concrete with the example you've probably seen before, and if you've seen it, you've probably seen it everywhere in machine learning, which is regularized least squares. So given some matrix that's m by n and some vector b of r of m, so we really have two objectives we care about. So those being the f1 and f2. So f1 is your standard least squares objective function. So we want to minimize ax minus b under the L2 norm. Now, this is a measure of how well your model is fitting the data. But in regularized regression, we also have this f2, which is the penalty on x. So this is measuring how small x is, and we want x to be as small as possible. Now f1 and f2 kind of pull against each other, so there's a fighting force. Okay, so we can write out the problem as a vector optimization problem, where the first component of the vector is f1 and the second component is f2. And since there's only two components of the vector and they return real values, our k, our proper cone, is the positive orthant in 2 dimensions. So r of 2 plus. And here are dimensions of our vector here. So this is a vector valued optimization problem. So let's do some scalarization and see what happens. Okay, so to find a Pareto optimal points, we scalarize with some lambda 1 and lambda 2 is greater than or equal to 0. And of course that looks like this. So this is a quadratic in x with positive Hessian. So we can solve it by setting the gradient to 0. So if we let mu, new parameter, which is equal to lambda 2 over lambda 1, we have the following. So we have this x solution here parameterized by mu, and look at the solution. To some of you, this might be familiar. This is the exactly ridge regression. The parameter mu is just the regularization coefficient. And now we have a really clean interpretation. Mu is a relative weight we place on keeping x small versus keeping the fit tight. So larger mu means we care more about shrinking x, so we get a smaller solution with a worse fit. A smaller mu means we care more about fit, recovering the least squares solution on the limit that mu goes to 0, right? This term goes away. Okay, so just drawing a quick diagram here, and this pseudo-inverse is this value here times b. So the curve is a Pareto front. So this x of mu over all values of mu, so you sweep it out and you get this Pareto front here. So this is the optimal trade-off. Every point on this curve corresponds with some mu greater than 0, some regression solution. Two endpoint solutions, the corresponding pseudo-inverse times b and x equals 0 here correspond to limits mu goes to 0 and mu goes to infinity. We're covering only the boundary weight vectors lambda equals 1, 0 and lambda equals 0, 1 respectively. So, ridge regression isn't just some ad hoc regularization trick. It's a method of scalarization applied to a bi-criterion problem, where you're generally trading off fit against solution size. So every choice of mu gives you a different Pareto optimal solution, and the full regularization path sweeps out the trade-off curve. All right, so that's 4.7. The big idea is once your objective is vector valued, you generally can't have a single best point. Instead, you get a Pareto front instead. Also, I want to highlight this principled, quote unquote, principled interpretation of regularized least squares. I thought it was really cool and interesting, honestly, to me, because I thought, well, it's much more satisfying than the explanation I got in my machine learning classes, which was basically we just needed an extra penalty to avoid overfitting. In my classes, I always wondered, why this penalty and not others. And finally, after like 6 months or so after graduation now, I see the underlying principle basically for regularized least squares. So anyways, that was just really eye-opening. So next week I'll be moving into chapter 5 actually. So that's about duality. That's really, where the, beauty comes in, if you want to call it that. Which is actually the last chapter we will study before moving to the machine learning textbook finally. The textbook actually hints at the end of the section that actually scalarization, which we learn about here, and Lagrangian duality, which we'll learn about later, are actually related. So that's something I'm looking forward to see how they actually are related. All right, I'll see you next week.